so today we're in the parametric equation. So if we have some function of x equal to f of t and y equal to g of t, then this is called a parametric equation because t in this case is the parameter. So in order to graph this, we find the value of x in a collection of t and y in a collection of t. Okay, so let's try to eliminate the parameter. So what if we have x over here equal to t minus 1 and y equal to 4t plus 1. Start easy first. So first let's eliminate t, which is what the parameter is. So for this, it can be easy. We can do t equal to x plus 1, and then we can substitute the t into the 4t right here. So we have y equal to 4, and then we can substitute t equal to x plus 1. So we can substitute that in. So it'll be x plus 1 and then plus 1. And then we have y equal to 4x plus 4 plus 1. And y will be equal to 4x plus 4 plus 5. Sorry, 4 plus 1 is 5. And that's how we eliminate the parameter. Okay, so let's move on with the slope and tangent line. So what do we do when we have the parametric form of derivative? So that would look something like this. This is the equation for dy dx equal to the dy dt over to dx dt. And this is a formula for a parametric form of derivative. So what if we want to find a second derivative? How would that look like? So pretty easy, the same old thing. 2 dx equal to dx, because we can separate the d out in the front the beginning. So we have dy, and then we separate the dx out, and we have a dx left. Then we and that will equal to, since we have a dt, we have dt over dx over to dx dt, and that will be the second derivative. Okay, so let's do some example. So what if we have x equal to t minus t over 3, y equal to 2t plus 5. So let's find the parametric equation for this. So we have dy dx, and just rewriting the equation now, which is dy with respect to t dx with respect to dt equal to, so over here, okay, so the derivative y with respect to x over here, which should be 2. Oops, sorry, that looked terrible. And then the derivative of x with respect to t will just be 1 minus 3t squared. Okay, so what if we want to find a second derivative, which is dy, which is dx squared. So the formula for that is just pretty long. D with respect to d dy dx with respect to t. Okay, I'm just rewriting the formula now. So d dt and dy dx is just the first derivative. So just rewrite that down. And then the bottom is x with respect to t, and the derivative of x with respect to t is just 1 minus 3t. And then since dt square. Okay, then let's focusing on just the numerator first. Without this mass, I'm rewriting that over here as dt 2 times 1 minus 3 t squared plus 1. So I'm just rewriting this in another form to make it easier to solve. So I move the denominator on the top with negative to the power of negative 1. So this will equal to negative 2 1 minus 3 t squared minus 2. I'm just doing the chain rule to do the derivative. So after using the chain rule, I got negative 2 1 minus 3x squared to the power of negative 2 times negative 6t over. Oh wait, and this is the numerator, and then we can completely simplify this into 12t over 2 1 minus 3t squared. So take that, multiply that, and then this going to the bottom with a negative 2 coming to the power of 2, which is square. So we rewrite that over here as 12t over 2 1 minus 3t squared over 2 over to our old denominator, which is 1 minus 3t squared. So now let's solve this. This can be equal to 12t over to 1 minus 3t squared times 1 over 3 1 minus 3t squared, and this, and we just multiply that. So 12t times 1 is just 12t, and then 1 minus 3t 1 minus 3 sorry, and then 1 minus 3t squared times 1 over 1 minus 3t squared. So that make it like a power of 1 right there. Make it 2 plus 1 is 3. So 12t over 1 minus 3t squared power of 3. And this is the second derivative. Okay, let's move on to vector value function. So first of all, start out with the function of the form of the plane is rt equal to ft plus gt, and then we have this form of space, which is, or the easier way to say that, the form space rt equal to ft plus gt plus ht. So if all this is a vector value function where f, g, and h are real value function of a parameter t, then the value function can also be denoted as rt equal to ft gt. And this is an easy way for us to write vector. Okay, so what if we try and take the limit of the whole vector where t approaches a? So if the limit of t of ft where t approaches a plus the limit of gt t approach a, then this proves that there is a limit of f and g exists in when t approach to a. Okay, so what are we trying to find if it's continuous? So if rt, if I first let me write the limit t approach to a, rt equal to r of a, then if the vector value of r is continuous at the point given that t equal to a, then the limit exists when t equal to a. And if r is continuous on every point of that integral, that means that the integral itself is continuous. Okay, so let's look at differentiable of vector. So the derivative of a vector value function r can be defined as r prime of t equal to the limit of delta t approach to 0, where r times t plus delta t minus rt over delta t. Okay, so what if rt is differentiable? What is the same as rt? Okay, so what if rt equal to f of t in the interval plus in the I interval plus g of t in the j interval? Then if f and g are a differentiable function of t, then r prime of t equal to f prime of t in the I direction plus g prime of t in the j form direction. So what if rt equal to ft in the I, it's go the same thing with space, so plus gt in the j direction plus ht k direction. That means that r prime of t equal to f prime of t I direction plus g prime of t in the j direction plus ht e prime of t in the k direction. So it's just saying that if this is differentiable at f, g, and h of t, then r prime of t equal to f prime of t I direction plus g prime t in the j direction plus h prime t in the k direction.